When talking about kinetic energy, it is important that you understand that the word kinetic refers to motion. So some body, whether it is small such as a molecule or large such as a car, it is the energy of a body in motion. Kinetic energy as an equation can be represented by either just a K or sometimes a KE, and it is equal to 1/2 the mass of what is moving times the velocity squared. And let's talk about these units. Kinetic energy is measured in the unit of a joule. And if you think about the units that mass and velocity are measured in, you can actually go back and think about what a joule really is as far as the units that are in its derivation. So energy is measured in joules, 1/2 is a constant, mass is measured in kilograms, and velocity is measured in meters per second. But those meters per second are squared in this case. What that really means is that a joule is a kilogram meter squared per second squared. Now let's think about the kinetic energy equation in a qualitative way. If you have two objects, one object is light and the other object is heavy, and they are moving with the same velocity, then the only independent variable is the mass, because the mass of one would be light and the mass of the other would be heavy. If the mass of the heavy object is, say, twice as heavy as the lighter object, then it will have twice the kinetic energy if they have the same velocity. Doubling m will double k. Tripling m will triple k. In another situation, you have two masses. Both have the same mass, but object A is moving twice as fast as object B. Although they have the same mass, the difference here is the velocity, or the speed. If A is moving twice as fast as B, it'll actually have 4 times the kinetic energy. With real numbers, it might be easier to understand. In calculating the kinetic energy of object A, we will do 1/2 the mass of object A, which is 1 kilogram, times the velocity of object A, which is 4 meters per second, and that square affects only the 4. The kinetic energy of object B will be 1/2 the mass of object B, which happens to still be 1 kilogram, times the velocity of object B, which is 2 meters per second, squared. 4 squared is 16, times 1 is 16, and 1/2 of 16 gives you 8 joules. For object B, 2 squared is 4, times 1 is 4, and 1/2 of 4 is 2 joules. It's clear to see that when you double the velocity, the object that has double the velocity actually has 4 times the kinetic energy. And that same rule applies for any ratio. That proves to us that it is not a linear relationship. If, for example, two objects with the same mass have different velocities, where the mass of one object is the velocity of one object is 3 times the velocity of the other object, then the faster object actually has 3 squared, which is 9 times the kinetic energy. Suppose you have two gases in a container at the same temperature, and these gases are behaving ideally. If the temperature of neon and argon mixed in a container is 300 Kelvin, then the first question is, which one has more kinetic energy? Which gas sample in the mixture has more kinetic energy? Would it be neon with an approximate molar mass of 20 grams per mole? Or would it be argon with an approximate molar mass of 40 grams per mole. If you write out the kinetic energy equation, you see that mass and velocity are next to each other, which indicates an inverse relationship. Although this inverse relationship is not a linear proportion, it is an inverse square proportion. The idea still holds true, though, that the higher the mass of something, the slower it moves if it has the same kinetic energy as another body. So, neon is lighter than argon. Argon is heavier than neon. However, if they are at the same temperature, then they have the same kinetic energy. So that's how we're going to answer the first question. The average kinetic energy of the molecules is the same for each because of the temperature. And that is your justification. Temperature is proportional to kinetic energy of the molecular sample, the average kinetic energy. The second question, which has a faster average molecular velocity? Now, although neon and argon are in a container with the same temperature and therefore have the same kinetic energy, they are not moving with the same average molecular speed in that container. Qualitatively, we're going to answer this with lighter equals faster. And because neon has a lighter molar mass, it would actually have a faster average molecular speed or average molecular velocity than argon. At this point, we're going to rearrange the kinetic energy equation to solve for velocity, which is something you will have to do on occasion. The kinetic energy equation, which of course is K equals 1/2 mv squared, can be solved for velocity using simple algebra. The first thing I'm going to do is multiply both sides by 2. Multiplying both sides by 2 gets rid of the half, providing the next step, which is 2k equals mv squared. The next step is dividing both sides by m. By dividing both sides by m, the next iteration is 2k divided by m equals v squared. And the last thing to do is to take the square root of both sides. Taking the square root of both sides isolates the velocity to just being v as opposed to v squared, and gives me my final form, which is the square root of 2 times the kinetic energy divided by the mass equals the velocity. This equation will prove useful if you know that 2 samples or 2 objects or whatever have the same kinetic energy and they have different masses. You can determine their actual velocity or their average velocity. It gets a little bit stickier when you talk about average velocities and Boltzmann distributions and such, but this is all you would need to calculate the velocity of most macroscopic things using kinetic energy and mass.